Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on database and statistical reasoning. Let's go ahead and get started with problem number 1. Problem number 1 says the inclusion of an outlier in statistical analysis will most greatly affect which of the following measurements? A says median, B says mode, C says mean, and D says all three are equally affected. Now, the inclusion of an outlier in statistical analysis actually affects the mean, median, and mode differently because of how each measurement is calculated. The mean is the average, and it's calculated by summing all of the values and then dividing by the total number of values. Since it includes every data point, it is highly sensitive to extreme values like outliers, which can significantly alter the overall sum and therefore the mean. The median, on the other hand, represents the middle value when the data is ordered. It is less affected by outliers because the median depends only on the position of values, not their magnitude, and extreme values are going to have minimal influence on the order of the data. The mode, this is the most frequently occurring value in the data set. It's not directly impacted by outliers unless the outlier itself becomes the most frequent value. But since outliers are typically rare, they usually do not affect the mode. Therefore, the mean is the most greatly affected by the inclusion of an outlier, and that means that the correct answer for problem 1 is C. Problem 2 says, in a sample of hospital patients, the mean age is found to be significantly lower than the median. Which of the following best describes this distribution? A says skewed right, B says skewed left, C says normal, and D says bimodal. During lecture, we said that when the mean is significantly lower than the median, it indicates that the distribution is skewed left. In a left-skewed distribution, also known as negatively skewed, the tail of the distribution extends more towards the left or towards the lower values. This occurs because extreme low values pull the mean downward, while the median, being resistant to outliers, remains relatively unaffected. And the result is a mean that is less than the median. That means that the correct answer here is B. Looking at the other options, a normal distribution would have the mean and median approximately equal, while a skewed right distribution would have the mean greater than the median. A bimodal distribution refers to a data set with two distinct peaks, which does not apply here. So once again, 2 is B. Beautiful, let's move on to 3. 3 says, what is the median of the following data set? Here we have the following numbers: 7, 17, 53, 23, 4, 2, and 4. The median is the central data point in an ordered list. Now, the first thing we want to do is obviously order these numbers in ascending order. So here we're going to have 2, 4, 4, 7, 17, 23, and 53. Now, this data set has 7 values. So it has an odd number of values. That means that the central point is going to be one single number. If this data set had an even number of values, then we would have 2 numbers in the middle, and to figure out the median, we would have to take the average between those 2 values. Here, we don't have to worry about that. We can start to eliminate the same number of values on both sides until we reach the middle. And that is how we get our median. For this data set, our median is 7, which means that the correct answer for problem 3 is B. Problem 4 says, on Santa Cruz Island, the available food sources lead to disruptive selection in the beak size of finches, in which large and small beak sizes were favored over intermediate-sized beaks. As a result, few finches have an intermediate-sized beak. If a sample of finches were analyzed, what distribution best describes the distribution of beak size? As a result of disruptive selection, the population develops two distinct groups, one with large beaks and the other with small beaks, and the intermediate-sized beaks become rare. This type of distribution is best described as bimodal, which refers to a data set with two distinct peaks or modes. In this case, the two peaks correspond to the population of finches with large and small beaks, while the intermediate region is underrepresented. This means that the correct answer for problem 4 is B. Looking at the other options, normal distribution, this is a symmetrical bell-shaped curve. It doesn't capture what this problem is describing. And skewed left and right also do not capture the dual-peaked nature of this distribution. So once again, 4 is B. Problem 5 says, a 95% confidence interval will fall within what distance from the mean? Approximately 95% of values fall within 2 standard deviations of the mean for a normal distribution, and a confidence interval is constructed using the same values. So that means the correct answer for problem 5 is B. Just as a reminder, approximately 68% of the values are within 1 standard deviation, and 99.7% are within 3 standard deviations. Now let's move on to problem 6. Problem 6 says approximately 20% of people who live in the US eat fast food at least once per week. A new study conducted by the National Heart Association showed that 48% of US residents have some form of cardiovascular disease. Which of the following hypothetical findings could be used to show that cardiovascular disease is independent of weekly fast food consumption? To determine whether cardiovascular disease is independent of weekly fast food consumption, we need to understand what independence means. 2 events are considered independent if the probability of them occurring together equals the product of their individual probabilities. So for this problem, A represents having cardiovascular disease, and B represents eating fast food weekly. If the joint probability matches the expected value under independence, then the 2 events are independent. Let's keep that in mind as we evaluate each answer choice. A says individuals who do not consume fast food do not have cardiovascular disease. So this suggests that avoiding fast food guarantees freedom from cardiovascular disease. And that suggests a strong dependency between the 2 variables. But independence means that the likelihood of cardiovascular disease should not depend on whether someone eats fast food. Since this statement implies a direct relationship between the 2 variables, it contradicts independence and is therefore not correct. B says, of the 48% of those who had cardiovascular disease, only half of them ate fast food on a weekly basis. Now, this statement describes the conditional probability of eating fast food given that someone has cardiovascular disease, but it doesn't provide the overall joint probability for the population. And without this value, we cannot test independence. So this answer choice is not correct. C says 9.6% of US residents have cardiovascular disease and consume fast food on a weekly basis. Now, this statement provides the joint probability. It's telling us that the joint probability is 0.096. And this value we need to test independence. So now to determine if the 2 events are independent, we compare this value with the product of their individual probabilities. The probability of having cardiovascular disease is 48%, so 0.48. And the probability of eating fast food weekly is 20%, written as 0.2. If we multiply these two values together, we get 0.096. Since the given joint probability matches the calculated value, the two events are independent, and this choice supports independence and is the correct answer. Let's still work through D. D says none of the individuals who consume fast food on a weekly basis develop cardiovascular disease. So this suggests a complete absence of overlap between the two events, which indicates a strong negative dependence. Independence requires that the occurrence of one event doesn't affect the probability of the other. So this statement contradicts the requirement and is therefore incorrect. Once again, 6 is C. 7 says, which of the following outliers would most likely be the easiest to correct? Let's go ahead and analyze each answer choice in detail to figure out which one is correct. A says a typographical error in data transfer. So this typically involves a really simple mistake in recording or transcribing data, like maybe entering an incorrect number or misplacing a decimal point. These errors are often easily spotted when the data is reviewed against the original source or when cross-checking the data for consistency. Since the source of the error is usually clear and the correction process is straightforward, this type of outlier is really easy to correct. It's actually the correct answer for this problem, but we're still going to work through B, C, and D. B says a measurement error in instrument calibration. Now, a measurement error due to faulty instrument calibration is more complex because it often affects multiple data points rather than a single outlier. And correcting for this kind of error usually involves identifying the exact calibration error, then recalibrating the instrument, and then possibly repeating all of the measurements. So while it can be addressed, it is significantly more time-consuming than fixing a simple typographical error. C says a heavily skewed distribution. Now, this is not necessarily an error, but rather a characteristic of the data. And correcting or adjusting for skewness often requires statistical methods, such as transformations or identifying underlying causes of the skew. So this process is analytical and far more complicated than resolving a typographical error. Finally, D says a correctly measured anomaly result. So this reflects genuine variability in the data, not an error. And it might indicate an unusual but valid observation that could require further investigation to determine its cause and or its relevance. Since it isn't an error, correcting or addressing this might not be very straightforward, and it might involve further experiments or additional studies or more reading up on certain material. So, reading through all of these options, A is the correct answer. It's going to be the outlier that's going to be the easiest to correct for. Let's move on to problem 8. 8 says, assume that blonde hair and blue eyes are independent recessive traits. If one parent is a carrier for each gene, while the other parent is a homozygous recessive for both genes, what is the probability that the first two offsprings will both have blonde hair and blue eyes? To begin, we know that blonde hair and blue eyes are independent recessive traits. This means that the inheritance of one trait does not affect the inheritance of the other. A recessive trait is expressed only when the individual inherits two recessive alleles, one from each parent. Now, in this scenario, one parent is a carrier for both traits, meaning their genotype is capital A, lowercase a, capital B, lowercase b, where the capital letters indicate the dominant allele and the lowercase letters indicate the recessive allele. Now, the other parent is homozygous recessive for both traits, so their genotype is going to be lowercase a, lowercase a, lowercase b, lowercase b. Let's first calculate the probability of inheriting blonde hair. This requires the genotype, lowercase a, lowercase a. Now, from the carrier parent, there is a 50% chance of passing on the recessive allele. So we're going to write that down, 50% chance. And then from the homozygous recessive parent, the offspring will always inherit a recessive allele, so 100%. To figure out the probability of having blonde hair, we just multiply the two probabilities. 0.5 multiplied by 1, this gets us 0.5 or 50%. Now let's determine the probability of inheriting blue eyes. This requires the genotype, lowercase b, lowercase b. From the carrier parent, there's a 50% chance of passing on the recessive allele. And from the homozygous parent, the homozygous recessive parent, again, it's a 100% probability. They will always contribute a recessive allele. So to figure out the probability of inheriting blue eyes, this is just going to be 0.5 multiplied by 1. This gets us 0.5 or 50% probability. Now, since the two traits are inherited independently, we calculate the combined probability of an offspring having both blonde hair and blue eyes by multiplying the probabilities of each individual trait. So this is going to give us 0.5 multiplied by 0.5, which equals 0.25 or 25%. This means there is a 25% chance that any single child will inherit both traits. Now, the question is asking us, what is the probability that the first two offsprings will both have blonde hair and blue eyes? For this kind of probability, the probability of each child remains independent. So each child has a 25% chance. Then for the both, we just have to multiply 0.25 by 0.25. This gets us 0.0625 or 6.25%. This best aligns with answer choice A. So the correct answer for problem 8 is A. Let's move on to problem 9. 9 says, based on the country level map below, which of the following statements best represents the data about individuals older than 65 in the US? The darker the shade of green, the higher the percentage of persons over 65. Let's work through each answer choice. A says most of the people over 65 in the US live in the center of the country. Now, this statement refers to the total number of people over 65 and not the proportion within counties. So this map, it doesn't show population counts, it only shows percentages. And while many central counties are shaded dark green, and that indicates higher percentages of older individuals, it's important to note that these areas generally have smaller populations. So this means the total number of people over 65 is likely lower in the center compared to the more populated areas like the coasts. So A doesn't seem like it's the correct answer. B says most of the people living in the center of the US are over 65. This statement claims that over 50% of the total population in the central counties is over 65. Now, the map doesn't support this conclusion. While it shows that the central counties have higher percentages of older individuals, they likely still represent a minority of the overall population in those areas. For example, even a high percentage like 25 to 30% would still mean most residents are under 65. So this is not a correct statement. Answer choice C says the center of the US tends to have a larger proportion of people over 65. Now, this statement aligns with the map. The central counties show darker shades of green, and that indicates a higher percentage of residents over 65 compared to the coastal counties. And this suggests that the proportion of older individuals is higher in these areas, even if the total number of older people is not. So C is going to be the correct answer for this problem, but we're going to read D anyway. D says there are more people over 65 moving to the center of the country than elsewhere. Now, this map provides absolutely no information about migration patterns. It only shows the percentage of older individuals within each county, and not whether people are moving into or out of areas. So there's no evidence to back up answer choice D. It's therefore incorrect. Once again, the correct answer for 9 is C. Let's move on to problem 10. 10 says, as the confidence level increases, a confidence interval becomes blank. A says become wider, B says becomes thinner, C says shifts to higher values, and D says shifts to lower values. A confidence interval is a range of values that is likely to contain the true population parameter. The confidence level indicates how certain we are that the interval includes the true parameter. For example, a 95% confidence level means we are 95% confident that the interval contains the true value. Now, as the confidence level increases, we aim to be more certain that the interval contains the true parameter. To achieve this higher certainty, the confidence interval must account for more potential variability, which results in a wider interval. This ensures that even with more variability, the interval is likely to include the true value, which means that the correct answer for problem 10 is A. Problem 11 says, which of the following measures of distribution is most useful for determining probabilities? A says range, B says average distance, C says interquartile range, and D says standard deviation. Standard deviation is the most common measure of distribution. It is the most closely linked to the mean of a distribution, and it can be used to calculate p-values, which are probabilities. And specifically, p-values are the probability that an observed difference between two populations is due to chance. So with that being said, the correct answer for problem 11 is D. Let's move on to problem 12. Problem 12 says, are there any outliers on the following box plot? To determine whether there are any outliers in the box plot, we need to use the interquartile range rule. Outliers are defined as any data points that fall below the lower bound or above the upper bound. Now, how do we calculate the interquartile range and the lower and upper bounds? Well, let's start with the interquartile range. This is the difference between the third quartile, Q3, and the first quartile, Q1. Now, we can calculate this because we're given Q1 and Q3 on the box plot. Q3 is equal to 2,280, and Q1 is equal to 2,075. And this difference gives us 205. This is our interquartile range. From here, we can calculate the lower bound and the upper bound. The lower bound is defined as Q1 minus 1.5 multiplied by the interquartile range. So this is equal to 2,075 minus 1.5 multiplied by 205. I'm going to approximate this to 200. 200 multiplied by 1.5 is 300. 2,075 minus 300 is equal to 1,775. Then the upper bound, this is calculated as Q3 plus 1.5 multiplied by the interquartile range. So this is equal to 2,280 plus 1.5 multiplied by the interquartile range. Once again, I'm going to approximate this to 200. 1.5 multiplied by 200 is 300. And 2,280 plus 300 is equal to 2,580. Now that we have our lower and upper bounds, any values that fall below 1,775 or fall above 2,580 are considered outliers. So from the data, 1,575 falls below the lower bound. Therefore, it's an outlier. And then this number, 2,600, that's above the upper bound. So it's also an outlier. Considering all that, the correct answer for this problem is going to be C. Are there any outliers in the following box plot? Yes, both 1,575 and 2,600 are outliers. Beautiful. We've solved this problem, and now we can move into problem 13. Problem 13 says, a gas station attendant notices that there are more lottery tickets sold on the days that a lot of ice cream is sold, and hypothesizes that the ingestion of excess glucose leads to an increase in risk-taking behavior. The attendant begins to tally how much ice cream and how many lottery tickets are sold on a daily basis to generate the graph below. The attendant analyzes the data and concludes that the hypothesis is true. Are there any flaws in this conclusion? A says no, the number of tickets sold increases as the pints of ice cream sold increase. B says no, the study is appropriately controlled. C says yes, the study is missing a positive control. And D says yes, the attendant has proved correlation, but not a causal link. Now, the correct answer for this problem is D, because the attendant has demonstrated a correlation, but failed to establish a causal link. The data shows that as ice cream sales increase, the lottery ticket sales also rise, which indicates a positive correlation between the two variables. However, correlation alone does not imply causation. Just because two variables change together does not mean that one causes the other. For instance, both ice cream sales and lottery ticket sales could increase due to an unrelated factor. So the attendance hypothesis, which claims that ingesting glucose from ice cream increases risk-taking behavior, is not directly tested by this study. The study simply tracks the quantities of ice cream and the lottery tickets sold without truly examining whether consuming ice cream specifically causes individuals to take risks like buying lottery tickets. Furthermore, the study does not account for other factors that could influence lottery ticket sales, like promotions or weekends or even local events, and it makes it impossible to isolate the role of glucose ingestion in this observed pattern. So that's all to say that, again, the correct answer for problem 13 is D. Let's move on to problem 14. Problem 14 says the following histogram blank. Statement 1 says contains a bimodal distribution. Statement 2 says should be analyzed as two separate distributions. And 3 says contains one mode. This histogram displays the height distribution in a high school class, and it's separated by gender. From the data, it's clear that the distribution is bimodal. A bimodal distribution occurs when there are two distinct peaks in the data. In this case, we see a distinct peak around here for the females and a distinct peak over here for the males. And these two peaks suggest that the data is composed of two overlapping groups, male and female students. So statement 1 is correct. Statement 2 is also true because the data should be analyzed as two separate distributions, one for females and one for males. The genders, they represent two distinct populations with different height ranges and different central tendencies. Combining them into this single distribution makes it hard to observe the patterns and the differences that arise based off of gender. Now, this third statement says it contains one mode. This is a true statement. There is indeed only one mode at 5, 6, and this is the measurement with the largest number of corresponding data points. So we see that statement 1, 2, and 3 are true, which means that the correct answer for problem 14 is D. Now we can move into our last and final problem. This problem says a cardiologist is investing a new drug therapy for the treatment of hypertension. The cardiologist measures the baseline blood pressure of several patients, then treats them with the drug for 10 weeks. And he measures their blood pressure again after this time. We see the data right here. Based on this data, should the doctor advocate for making this drug the standard treatment for hypertension? A says yes, there is a statistically significant decrease in blood pressure. B says yes, the drug is effective at decreasing blood pressure. C says no, while statistically significant, the results are not clinically significant. And D says no, the data is not statistically significant. Now, the data shows that the drug reduced both systolic and diastolic pressure with p-values of 0.01 and 0.03, respectively. These p-values are less than the common threshold of 0.05, which indicates that the results are statistically significant. So this means there's a low probability that the observed changes in blood pressure occurred by random chance, and we can reasonably attribute these reductions to the drug's effect. However, statistical significance does not necessarily imply clinical significance. Clinical significance refers to whether the magnitude of the change in blood pressure is large enough to have a meaningful impact on the patient's health. For example, while the reduction in blood pressure might be statistically detectable, the absolute difference may not be substantial enough to improve outcomes for patients or to even justify the drug as a standard treatment. And these graphs, they suggest changes that are relatively small, which may limit the real-world relevance of this drug in treating hypertension. To add to that, before advocating for this drug as the standard treatment, it'd be important to consider other factors, like what are the side effects? What is the cost going to be? And we should compare it with existing treatments. A statistically significant result alone is insufficient to determine whether a drug is the best option for patients. All that being said, the correct answer for problem 15 is going to be C. No, while statistically significant, the results are not clinically significant. And with that, we've completed this practice problem set, and we are done with this playlist. Please let me know if you have any questions, comments, concerns down below. If you found this playlist helpful, please let me know so I can continue to make MCAT content for all of you. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors. I love you all.